Hi everybody. In this section we're looking at composition of transformations. So what is a composition? Well, if we perform more than one rigid transformation on a figure, it's a composition. So rigid meaning it's an isometry or it's a congruent figure. So we're not going to do a dilation, shrinking it, or blowing up. The figures that get transformed are going to be congruent. So a glide reflection is a type of composition. So we take a reflection and a translation when we're doing a glide reflection. The translation is in a direction parallel to the line of reflection. Okay, so let's take a look at example 1. We're going to reflect triangle ABC over the y-axis and then translate the image 8 units down. So these are two transformations. We're doing a reflection and then a translation, or we could say this is a flip and a slide. So I have triangle ABC is already plotted here. I'm going to reflect it over the y-axis. So it's going to be equidistant from the point to its prime point. So now it's reflected. And now I'm just going to take A prime, B prime, C prime and translate it down 8 units. So slide it down 8 units. So I got A double prime, C double prime, and B double prime. So what I want to do in example 2, I've already done example 1. Example 2, I want to write a rule that describes the composition of the transformation. So A, B, C, here are my coordinates for the original, and it's going to transform into the A double prime, B double prime, C double prime. What do you notice about the coordinates? The x coordinates on all of these is negative, the opposite. From 10 to negative 10, 8 to negative 8, etc. Look at the y coordinates. What's happening there? Well, each one of them are 8 less in the double primes. So I can write my rule here. I'm saying that xy transforms to negative x comma y minus 8. I think it's really useful to write down the coordinates of all the original to the transformed figure so that you can kind of see how the rule goes. So now we're going to do some reflections over parallel lines. For example 3, we're going to reflect ABC over y equals 3 and then y equals negative 5. So I'm going to draw the lines here. Y equals 3 and y equals negative 5 are horizontal lines. And I'm going to reflect ABC first over y equals 3. So the prime points are going to be equidistant to the line as the ABC points are. So here's my first reflection. And then I'm going to take this figure and reflect it across y equals negative 5. I'm going to do a double reflection here with parallel lines. And you see that the A, B, C double prime points are just basically a transformation that is equivalent to a slide or a translation. So we can see this better if I write down the points. Here's my original ABC, and here are my double primes. Notice the x coordinates don't change. The only thing that changes are the y coordinates. The y coordinates are becoming less, each one. So you can just figure out how much less. It ends up being 16. 16 less, so that slide is going down. So my rule is xy translates to x comma y minus 16. There is a pattern here. You can see the distance between the two horizontal lines is 8. And then the distance we did the translation is 16. So the theorem for reflections over parallel lines is if you compose two reflections over parallel lines that are h units apart, in this case 8, it is equivalent to a single translation of 2 times h units, which would be 16. And that's going to be useful in the next example. So example 5, triangle DEF has vertices of DEF. There they are written there, so I'm going to plot them. 3, -1 for D, 8, -3 for E, and F is 6, 4. I'm going to do a double reflection here. First over x equals -5, and then x equals 1. Well, I gave you the graph here, and I'm plotting it to start off, but it's going to go off the graph. But we can write these down. We can start it out here so we get a general idea of what's going to happen. So remember that x equals a constant is a vertical line. And so I've got them both plotted. We can see they're 6 units apart. So first we're going to reflect over x equals -5. So here the red arrows are showing that reflection. And then we're going to reflect across x equals 1. So the combination of the two reflections will be equivalent to a translation of 2 times 6 units to the right. So 2 times 6 because that's the difference in the two vertical line reflections. So 2 times 6 is 12, so my rule is xy translates to x plus 12, y. Y doesn't move anywhere. So here are my double prime coordinates here. I think I wrote it as a prime, but that should be a double prime. And you can see the x coordinates are the same and the y coordinates we're adding 16. So in example 6, we're going to use the same triangle DEF, but we're going to reflect it over the x-axis followed by the y-axis. So in this case, these two lines aren't parallel. In fact, they're perpendicular to each other. So let's first do the x-axis. A little tricky here because the figure lies on the x-axis, so the points on the bottom side reflect to the top, the points on the top reflect to the bottom side, and I'm going to color this yellow so you can see this is my prime triangle. Now we're going to reflect the yellow triangle over the y-axis. Let's zoom in here so we can see this a little bit better. So the points are going to be the y-axis is going to bisect the point and its prime point. Let's color this in orange. So I've done 2 reflections here, one over x and the other over y. And it's the same as what? Well, let's write down the points so we can get a general idea of what's going on here. So here my original triangle DEF, and it translates to the double prime point. So notice here, D is 3, -1. D double prime is -3, +1. E is 8, -3. E double prime is -8, +3. So you see that the coordinates are the opposite of the original. Now this is the same as a 180-degree rotation through the origin. So this composition of reflecting over x and then the y-axis is the same as a 180-degree rotation. So that's what we're going to write for this theorem, the reflection over the axis theorem. If you compose 2 reflections over each axis, meaning the x and the y, then the final image is a rotation of 180 degrees through the origin of the original figure. Okay, so I'm going to stop right there with part 1. I guess make part 2 another video because I got to do construction by hand, and then I'll continue a little bit on the computer. So go back and review any of this as you need. If not, go on to part 2.